Yeah.
Okay.
Okay.
So
Yeah. Yeah. Sorry. I want to introduce you since I'm organizer. So
you said, of course, of course.
yeah. Thank you for interruption. I I think sorry for interruption. Yeah.
No, no.
Yeah. Let me start our seminar. Today's speaker is Gianluca Lagnese, right? Yeah.
Lagnese, yeah, so it's okay.
Yeah, yes. Yeah, and he's from Joseph Stefan Institute.
Mhm.
Yeah, please start when you're ready.
Okay, okay, okay. So nice to meet you all, and I'm glad for the invitation. Okay, basically, so the topic is this like confinement and forced vacuum decay, the way we understand this phenomena in the context of quantum spin chains. Um, so I'll try to give you an overview of, let's say, how this is occurring or in this context. Of course, like what happens in quantum spin chain resembles in general what happens in the context of solid state physics. So so the idea behind quantum spin chain, also the thing why essentially they are maybe interesting objects to some extent is that so there is like they're at the center, let's say, between three main, let's say, point of strength. So one is that, um, can you see my, no, I don't see it. Okay, just a
Uh,
second.
yeah, your cursor, you mean?
Yeah,
You
my cursor, because I don't see it.
now, yeah, me too. I cannot see your mouse cursor.
Yeah, I can only see over the, this is strange. Just a second.
Yeah,
No, it disappears here. Oh, this
yeah,
is strange.
disappear. Yeah,
Just a second, sorry. Let's do like this, okay?
yeah. Okay, okay. Yeah.
I'm sorry. Oh, for the
No, it's okay.
inconvenience.
It's okay. Yeah.
Okay, and then it's like, let's see if this is working here. I don't know. Whoa,
Uh,
no, you don't see the proper screen. Okay, sorry.
yeah,
Let's go back to the first thing.
yeah.
Uh, I don't know why it disappears. I'm sorry for this.
No, it's okay. It's okay. Yeah.
I'm just exporting them as a normal PDF because maybe there is
Mm,
something I don't understand about this um,
mm.
keynote that is like behaving weirdly. Okay? Okay. Okay. Almost there.
Yeah. Please don't launch. Yeah.
Okay, now
Yeah,
you
we can
see.
see. Yeah, we can see. Yeah.
Okay, sorry. So let's go. Oh my God. All right. But why it's so okay.
Mm,
So okay, here we are. So I was saying, so essentially there is like a huge set of analytical tool, okay, whether they're coming from the context of quantum integrability, conformal field theory, blah, 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 and so on and so forth. So basically, this is like a Younger-Baxter equation, which is like a fundamental building block of the context of integrability in the context of so exactly solvable models in statistical physics. There is also like a huge array of numerical methods that are extremely efficient in the context of quantum spin chain. And also, I mean, also the point of, so they're quite well understood now. So essentially, the point of strength is that we are extremely aware of what are their limits in the dynamics, in simulating the dynamics of these models. And also now there is like, there are many possible experimental setup that they can realize essentially the dynamic of up to a certain accuracy, the dynamic of quantum spin models. And the thing is that these experimental devices are also candidates of possible candidates for, let's say, quantum computers. Because essentially, quantum spin chain, in a sense, they are like a natural counterpart of these quantum devices. In the sense, the degrees of freedom are exactly mapped in these like qubits, where there are qubits that are like realized with the technology of Rydberg atoms or trapped ions or also superconducting qubits. So, essentially, the thing is that all these three points, they can like help each other and benchmark each other, you know, in order to progress, especially in order to make this possible quantum candidates for quantum computing to be further improved and perfected. So, okay, let me go for an overview then. So let's say the talk is more or less a first part where I introduce you to the model. I'll try to be as much as generic as possible. Then there is one part which is like mainly based on this work, which I would like to present you because it's like encodes like this idea of observing this phenomena, but in like a real-time setup. So in like a real-time evolution of the system, which is in a very, let's say, non-equilibrium setup. And then we will focus on this for work on false vacuum decay. So let's say, so the idea behind spin models, you probably may, of course, know all this. So I hope it's not to be too trivial. But essentially, okay, the thing is that we're introduced to explain magnetic properties of materials, and especially to understand like ferromagnetism, which is essentially the presence of spontaneous magnetization. So the material like show some spontaneous magnetization, even if like you don't apply any external field. And then why the spin? So one of the main origin, like at the microscopic level in the context of solid state physics, it's like the exchange interaction between the electrons. So I'm going to explain a bit this, but it's not that important. It's just to give you an idea of the background. And then basically one of the simplest generalization of possible models that we can draw out of this like exchange interaction based spin models is like the Ising model, which was extremely successful because it's like the most simple model that can show this phase transition, you know, from ferromagnetic to paramagnetic. And this phase transition is important from our point of view because in order to realize this, like, so the presence of confinement and false vacuum decay are intertwined in these models with this phase transition, because basically we need another phase to get like the to observe, so to get this model show this phenomenon. Okay, so the exchange interaction, so in a very simple setup, we understand it like this. You know, you put two atoms together, or you have like the protons and the electron clouds, and then what happens? So you want to describe essentially you want an Hamiltonian which is describing the energy level of the system of the electron cloud. And so what happens is that you have, let's say, an Hamiltonian which is describing like the bare atom, so when they're well separated. So this is for one atom, the other atom, and then we have the interaction. And then you want to solve the eigenstate equation. But you have a constraint. Essentially, you have your wave function, since these are electrons, must satisfy this like that if you exchange the electrons, you have to get a minus signs because you have their fermions. So this wave function is encoding both in this like spatial and like spin configuration. And of course, S equals 0 is antisymmetric and S is equal 1 is the symmetric triplet. So in order to get this property of the wave function, you need to account for the property of symmetry of the spatial wave function and the spin configuration. And then what you do is essentially that you solve the eigenstate equation for, let's say, the single item. And then you can write two possibilities. You know, this one where the spatial part is like symmetric. I'm basically skipping like the normalization here, or if you want, it's encoded here. And the other one is anti-symmetric. And then here you have like the spin component. Okay, so overall, this is satisfying this satisfies this requirement that we have here. And then what you can do, we can basically compute the expectation value of the whole Hamiltonian over these two configurations. And we see that there is like an energy difference, which is basically coming from the property of symmetry of the spatial component. But we can somehow break down as like in a spin language. So we can like explicitly break down something that is depending on the spin configuration. So this is the scalar product. And where the energy scale is essentially just given by the energy difference between the two configurations, the singlet and the triplet. So effectively, we can imagine that, like if when we place these two atoms together, we can write down some effective energy functional that it's depending on the spin configuration of the electrons. So like in a direct way, we get this like dependence on the spin. And this is basically one of the most frequent at the level of the solid state physics. But then, okay, how we get the easy model, basically the easy model is like you simplify. So because this is isotropical, okay, because it's a scalar product of the vector of this operator that represents like the spin in the three-dimensional space. And then basically you just assume somehow that this is not isotropical anymore. So you neglect the other component, you take only like one component. And here you get is how you get the Ising energy contribution. While this one instead is like the Heisenberg energy exchange term. And then what you do, basically you assume that your model, so when you place many atoms together, you assume that this still holds, but then you have to sum up over all pairs. Just a second. Sorry, I get some noise from the street.
Ah, I see. It's okay.
So you sum over all pairs. So essentially you have like this is living on the lattice. And then in any lattice position, you have one as J, one as I. And then on the links, basically you get the interaction term. So basically J represents the interaction between two Boring lattice positions. And okay, this essentially, as I already mentioned, this is like already an interesting model because we know that, let's say, two or more dimensional space, you have like a phase transition, a thermal phase transition, which is occurring at a certain temperature from ferromagnetic to paramagnetic phase. Paramagnetic, of course, means that essentially the model shows some spontaneous mobilization. So if you compute the expectation value of SZ, over your system, then it will be different from 0. And then now we want to get the other step. So basically, we said this is classical easing. Here I'm dropping the, let's say, the Z direction, let's say for simplicity, but essentially this is like the Z component. So we said it can have like two values, but then we want to go quantum. So how do we get the quantum model? So we go back to Pauli operators essentially. So that are the spin operators. And for example, you can pick up this SI to correspond to the sigma Z direction. And then we add something that is called transfer field, which is essentially it's called transfer field because it is in the orthogonal direction with respect to the interaction term. Okay, so because the interaction term is along Z, this is along X. Actually, you can still put along Y, is still okay. So it's like usually it's written this way, or sometimes you will find XXZ, but it's not that important. They're all equivalent. It's just like change of names. And what happens here? So first we say, okay, we have a thermal phase transition. But in this context of like quantum spin chain, we often work, okay, at 0 temperature, basically. So we imagine to be like full quantum, okay? So in this sense, the competition between this transfer direction and the Z direction of the interaction term is giving you the quantum fluctuation. So effectively, Hx is controlling the quantum fluctuation. So it's kind of playing the role of temperature for the thermal theory. And what happens is that here we have a graph. So we have like the thermal direction, and then we have like the Hx direction. At t equals 0, we have again like some ferromagnetic to paramagnetic phase transition, which is at Hx equal 1, which we call quantum phase transition, and is basically equivalent to the 2D classical thermal phase transition. So somehow the difference is that in this case, it's a property of the ground state. It's dramatically changing when you, let's say, tune your transfer field across this phase transition. And there is like very good book about this quantum phase transition, which has the same name. But essentially, it's like there is this quantum to classical correspondence for which like the 1 + 1 dimensional quantum phase transition is like equivalent to the 2D dimensional classical thermal phase transition. Okay, but other than that, for as far as we are concerned, is that we need to have like this ordered phase, which, as I said, occurs when the transfer field is less than 1, for which essentially you have like 2 degenerate ground states, which I resemble with like this all aligned spin. And then here, let's say I kind of show you like this kind like Landau-Ginzburg picture, but like this can be understood formally, but in this case, it's really like to guide through the intuition of what's going on, okay? Somehow we have like a free energy landscape if you want, and then the two minima are that corresponds to these two ground state, which are related by a Z2 transformation, so you only flip to all the spin. They are degenerate, so they are exactly the same energy level. So one thing that you can do to study this model, you can work like in the very small Hx limit, but of course we can be more general, but this is very useful to guide your intuition. So essentially, this configuration, which we can kind of call classical configuration, because basically all the spins are aligned, okay? So they're not like, they are not overlapping if you want. Or if you want, if you compute the expectation value of sigma z, the average over or expectation value of sigma z over the system is exactly 1. And then you can write down some kind of perturbative Hamiltonian of Hx, which is describing the dynamic of this domain wall excitation, which are the fundamental excitation over these two ground states. So basically, the thing is that if you put your system in one of these ground states, the excited states are these domain walls that are called like this because are domain between two configuration of the spin field. And let's say the interface, if you want, is exactly the position of your domain wall. And this term here is basically just giving you the hopping, so the dynamic. So if you apply this part here, this is making like this object jumping right and left. So this will give you the dynamic of the model. While this part here is just counting the number of domain wall that you have like, in your system. And two is essentially just because, because you have an interface, this is frustrated. So from this part here, you get an energy price, which if you want, it's the mass of your excitation. Okay, but as I said, we can be more general. And if you're interested, this is very standard technique. If you're interested, I can tell you more. But the main idea is that you can map this like model of spin, so this Pauli operator. You can use this like a Jordan-Wigner mapping, which basically it's mapping these operators to fermion operators. So it means that basically they are like satisfying like fermionic anti-commutation relation, and from there you do Fourier transform, Bogolyub rotation, and then you can write down the Hamiltonian in this diagonal form. So basically, you can decouple the modes. You can find these like fundamental modes that are like encoded in this momentum K. And then you get some dispersion relation, epsilon K. And this works for generic HX. But as long as, because we want to be in the ordered phase, as I said, so we still want some spontaneous magnetization. So as long as HX it's less than 1, because remember 1 is the phase transition, you have that your exactly degenerate ground states, they still show some spontaneous magnetization, which is given by this value, by this form here. And your domain wall excitation are basically interpolating between the two. So you still have this notion of domain walls. It's just that they're not interpolating by, let's say, from m-1 to m1, but to something that is like different from 1, but still greater than 0. And the mass gap also gets corrected. So the energy cost is not anymore 2, but it's 2 times 1 minus hx. But you still have this intuition of the dynamic. So this like picture that I showed you, let's say that in principle works only on small transversal limit, is still like very useful to guide our intuition. But now what happens is that what we want to do is that we add this longitudinal field. And the effect of this longitudinal field is that you break this symmetry between the two ground states, and you have introduced some finite energy density between the two ground states. And because of that, okay, we say that, okay, the most energetically favored minimum, we call it true vacuum, while the metastable vacuum, so the well that is higher in energy, we call it false vacuum. And the energy the density difference between the two is given by this factor, 2m style. So with again, m is like the spontaneous magnetization, and hx is just like the longitudinal field. Okay, so let's say what I will show you is what are the effects in the dynamic of the model after this field is like added.
Sorry,
So
I
now,
have a very naive question.
yeah, sure.
Yeah. In the previous slide, maybe 2 page before, 2 page before, yeah, you have shown about the figure of in the figure the arrows are not aligned, but
Here,
yeah. What is the difference to these non-aligned arrows and then aligned
guys,
arrows?
just to get you the idea is that
Mm,
so the idea is that in this, if you want, so if you are in the hx equals 0 limit,
yeah.
basically you can imagine, so you remember, so you have a lattice, and then on the lattice you have these pins.
Mm,
So you can forget about this term, you only have this interaction term, and then
yeah.
the configuration, the energetical configuration of the model are basically like just spin up, okay? So it's just, it's called also computational basis. So essentially
Mm,
you have, if you want that the Hamiltonian, it's already diagonal in this
yeah.
exact picture of spin up and down, okay?
Mm, mm,
When you add this field, and this field is non-negligible, what happens is that you have a competition between, okay, this three-dimensional space of, if you want, of, it's called block sphere,
mm,
and you have a overlap. So essentially, you have overlap between up and down, okay,
mm,
configuration.
mm, mm.
So your eigenstates of your model, they're not all fully polarized. So you cannot
Ah, I
represent,
see.
they're not fully polarized, but they are a little bit like some local combination of up and down,
Mm,
which still favors some direction, but
mm.
is not fully polarized along the z direction, okay?
Ah,
But
then
the
can
project,
yeah, yeah, yeah.
okay, so the projection along z is basically still this m, so it's still finite, but they also
Mm,
have some overlap with the xy plane if you want,
mm,
okay? So this is the
mm.
idea. It's just okay. This is just so I was trying to give an intuitive idea, okay, that you have like somehow adding fluctuation. This is like
Ah, then
okay,
can I
which
imagine the value h as to be temperature?
yeah, essentially that's
Yeah.
what they said. Somehow this is like the source. So this hx is like somehow equivalent to temperature in a sense,
Mm,
because
mm,
the temperature gives you thermal fluctuation. This hx is giving you like this quantum fluctuation. Quantum
mm,
fluctuation are basically are understood as the fact that the system is like in some quantum overlap of configuration. Okay,
I see, I see.
so it's
Thank you.
not
Yeah.
a product state of all up. Okay, but it's like
Mm,
some linear combination of
up and down.
all up, but also some down somewhere. Okay. Of course,
Yeah.
when you cross the phase transition, so when you cross hx equal 1, basically it's like completely random because you're going, so it's kind of your system is going in the x direction. So in the hx limit, where
Ah,
where it's basically hx is infinitely large,
mm,
basically everything is polarized along the h direction, sorry,
ah,
along the x direction, and basically you have like a product of like 1 over square root of 2 of up and down locally,
yes, yes,
because
yes.
you're completely rotated, okay? In
Ah,
this case, the z direction is still favored because you're in the order phase, but you have
mm,
fluctuation,
yeah, yeah,
okay?
yeah.
This is more or less the
Ah,
idea.
I see, I see. I completely understand, I think. Thank you. Yeah,
Okay, you're welcome.
yeah.
Okay, so now we can start with like the first topic, which is like this confinement. I mean, I know you're probably more interested in the second part, but like this is just good to give you also to introduce some concept, okay? So generically, what happened is that people like just observed that there are certain ferromagnetic material that when you introduce some external field, um, by doing some neutron scattering experiment or Terex spectroscopy, they were observing this like discrete peaks appearing in the spectrum. And this was done in these works. And this was one of the experimental evidence that something was going on in these ferromagnets. Of course, these are not ferromagnet, not all these ferromagnets that can, like say, accurately be described by Ising model, okay? But still, the idea is always there. So everything I'm going to explain you is still there, even like of course, there are not everything can be easily captured by the Ising model at the microscopic level. But there are some material that like they're to some extent well described by the Ising model. And in experiment, okay, so they observed the occurrence of these peaks. And also what happened, there is like this pioneering work, McCoy Wu, basically where they were studying, actually here in this case, it's like an Ising field theory. So it's the scaling, I can tell you more if you want, but the idea is that it's like the scaling limit of your model of the Ising chain that is on the lattice. And they were, by doing this, they were studying a two-point function, and they observed that like this is thermal theory again, that like when you are in the ordered phase, so basically the temperature is less of the, is smaller than the critical temperature. They were observing like this tower of poles appearing in the two-point function. So these are, let's say, historically the first evidence of, from the theoretical point of view, of this phenomenon. But in our case, as I said, so we want to address this like for phenomena in a real time out of equilibrium settings. Okay. And so this everything we're going to do, it's like a real-time evolution. So it's like imaginary time, sorry, not imaginary time. So it's like a unitary time evolution of your system. So in real time. And the system that we have in mind is like they are isolated. Okay. So basically, as I said, it's like pure unitary. So there is no coupling to environment. And which is, of course, this last point is intertwined with the first one. So we are at zero temperature, as I said, okay? So we are only concerned about quantum fluctuation, okay? This is very, I know it's very artificial to some extent, but the thing is that, and this is good review about this, all this corpus of work that has been very intense, and actually it was really motivated by the experimental advances in the cold atom techniques, because the idea is that laboratories were beginning to be able, this like now it's more than 10 years ago, they're beginning to be able to realize this setting, okay? So to like some kind of, so do some kind of real-time evolution of many body quantum system with a good degree of isolation from the environment and a good degree of coherence, so of unitary time evolution. So this opened like a whole line of research that studied this problem of real-time dynamics of isolated quantum system, many body quantum system. And out of this, okay, so the this idea of quench, so this all that is behind like this non-equilibrium setup is encoded in this protocol, which is also experimentally relevant because somehow experiment can realize this protocol, is that somehow you prepare your ground state. So you pick up a certain Hamiltonian, and your Hamiltonian depends on a set of parameters. In this case, in our case, these parameters are like hx and hz. And you prepare the ground state of your many-body Hamiltonian. And then what you do is that you suddenly change the parameters at a certain time, which we call t equals 0. Of course, experimentally, this is a bit harder, but the thing is that as long as this is fast enough, it is okay. Okay, so it's like to this extent, it's like it's still feasible in the experimental setup. And then when you change the parameters, you get new Hamiltonian. And what you do is that you evolve your Hamiltonian, you evolve your system from the initial state. So the ground state of the previous Hamiltonian, it's evolved with the new Hamiltonian. And this is like the quench protocol, essentially, which is idealized, but as I said, is also to some extent practical. And it's kind of somehow the standard protocol to drive your system out of equilibrium. And what we understand, so what I'm going to explain is like to intuitively there is this thing called the quasi-particle picture. So for models where you can find like well-defined quasi-particle states, so which are in our case basically are these domain walls that I described at the beginning, that are basically well-defined modes with a certain dispersion relation. The thing is that our understanding of the majority of what happens is that you imagine that like the initial state, it's like as a source of quasi-particle excitation. And then they propagate different, so if you have translational invariants, these are created in pairs and they propagate in like opposite direction. But if you assume that there is also a maximal propagation of speed, so essentially the speed is the derivative of the dispersion relation with respect to the momentum. If you assume that there is like a maximal propagation of these particles, this is called the Lieb-Robinson bound, which for local Hamiltonian basically is always true. This is like related to the property or locality property of the Hamiltonian. But as far as in this case, we have like a short range interaction because actually we have like only nearest neighbor interaction. So this is basically true in this case for sure. What happens is that these particles that are created within some correlation length that they call Xi, they will start carrying like a quantum correlation across the system, okay? And then we propagate. And then at any time, basically, the system within this, let's say, light construction, you can see like correlations. Outside this light construction, which is so basically outside of this like this distance that has been traveled by the maximal propagation speed, that basically you have like no correlation. And then the other thing basically that we have to see, so it's like how do we understand the long-time relaxation of the system? So imagine that this is your spin chain, but like some kind of in some thermodynamic limit. So you have a subsystem A and this complement A bar. So A plus A bar is the whole system, okay? And you consider a subsystem which somehow at a certain time t, so if t is long enough or this subsystem is small enough, what happens is that you can define an object, which is the reduced density matrix of the system. You can trace away the degree of freedom. So you basically trace away the degree of freedom of the complement, and you get a density matrix of your subsystem A. And there are two basically main kind of system. There are also other ones, but as far for us, it's I just want to say that there are two main outcomes. One is this, let's say, thermal chaotic system, where basically you can locally, so in this sense, your reduced density matrix behave like a thermal density matrix. So in this sense, this system, even if they are closed system, and the dynamics is unitary, so the whole system stays pure, but locally, so if you just look at the able to access at a small subspace of your system, essentially what you see is a thermal behavior for this kind of system. While for integrable system, we understood that there are like an infinite amount of conserved quantities that are this I, J, and charges, lambda J, that they constrain the dynamics. So this generalized Gibbs ensemble is introduced in this case, basically where you, in the first case, you only have the conserved quantity which is the Hamiltonian. In this case, you have infinite number of conserved quantities that are constraining the dynamics. The long-time relaxation, it's happening in this way. So it is like a generalized Gibbs ensemble sense. Okay, so then we can go to the first, let's say, effect of this longitudinal field in the dynamics. So one thing is that if you compute like the, as a first question, how much do I have more or less time or left? Because
Maybe you have 20 minutes, but you don't need to consider the time limit. Yeah.
okay, but sorry, maybe we lost a bit time at the beginning, so I have a feeling
Mm.
I'm running a bit late. So, okay,
Yeah,
let's
yeah.
go quickly through this part. So essentially, you monitor, for example, so you do this quench protocol that I showed you before. The quench protocol is this one, okay? So you start, as you see, the transfer field is kept in the region where the phase is ordered, but we turn on the longitudinal field, which is this one. And by turning on the longitudinal field, we see that like the local magnetization start behaving in a different way. So basically this is numerics, which is done with different like numerical techniques. And in comparison, you can see what happens when the longitudinal field is like it's off. So this case, you have like oscillations and slow relaxation. In the other case, it goes down exponentially. This is something that is like exactly computable in the case of the easy model, okay? And so how do you understand this? Essentially, as I said, the idea is that the initial state with this protocol is not anymore an eigenstate of the new Hamiltonian. So when you perform unitary time evolution, you can actually expand over the basis of H1. So expand over the eigenstates of H1. And then you have that your system evolves in this way, right? But then when you compute an observable, you will see that the observable is sensitive to the energy difference of these eigenstates. So if your system is developing like a discrete eigenstates, due to this longitudinal field, that these are this eigenstate that we will call meson in this sense, basically they will show up in the dynamics. And how do we see this even better? We perform like a Fourier transform, and then after the Fourier transform, we have these peaks, and these peaks are like actually they can be predicted to some extent with a two-body model. Okay, so again go back to this like fully polarized picture, but as I said, you can be more general, and then you can basically imagine so which energy I have associated to this configuration. I have like 2 times the mass of the gap of the domain walls, plus this long-range interaction, which is introduced by the finite energy density which between the two state, the two vacuum, okay, that I get when I turn on the longitudinal field. And then I can get this like two-body model. And if I essentially, I can write down like to be more generic, a kind of effective two-body Miltonian, which I can solve. And then from this, I can like take out the prediction of these masses. And they work out pretty good, okay? So next effect instead that we want to see is that in the connected correlator. So as I said, we have this quasi-particle picture that is saying that we locally create particles and they propagate. And this quantum correlation that is brought across the system from these quasi-particles, like it can be measured by these connected correlators. For example, like the one along Z, but it's not necessarily along Z. And what happens is that, what you can see is that from Hz equals 0, no longitudinal field, when you turn on your longitudinal field, basically this dynamic gets constrained. And you see less and less propagation of quasi-particles. So this light structure that can be like seen in real-time dynamics is basically shrinking. But then we can do something better. Basically these first 3 plots are the same plot as before, just with a different scale to highlight what's going on. Okay, so you can still see that are like there is some residual like construction. This residual like construction is basically given by pairs of mesons that are propagating because they are like here you don't see because like the signal is too weak because there are few of them. So the biggest signal is given by mesons nucleated, like isolated, but so pairs of domain walls. So two particles that are nucleated and they propagate. But here, basically, these are, if you want, are four particles that are propagating. So these two metons, they are still like particles with their respect, let's say, kind of dispersion relation. They propagate, but they're slower. So the light cone it's like smaller than the light cone with h equals 0 because these are heavier and small and they propagate at a slower speed. And then the last one that I'm showing you is just that if you instead are like in the not in the ordered phase, basically the phenomenon disappear. So in order to see it, so you get some qualitative difference, but you don't see this change in the light cone structure when you are like in the disordered phase, so above the phase transition. So I think, so this was some experimental observation, but maybe I can go ahead probably. So if you're interested, I can go back to this, but I will go ahead to the Volkswagen decay part.
Can
Just
I ask
because,
a question?
yeah, sure, of course.
So let me check my understanding. So in the quantum Ising model you introduced, you have two parameters, hx and hz.
Okay,
And when hz is 0,
yes.
is the system solvable or
Yes. When which hz, the longitudinal field is 0, the system is solvable in the sense that I explained before. Basically, you can do this Jordan-Wigner mapping, and then you have like this fermionic
okay,
degrees of freedom, and then you have this free fermion Hamiltonian that you can exactly solve.
I see. So essentially the system can be diagonalized.
Exactly. When
Okay,
you put the longitudinal field, you cannot do anymore. You cannot
okay,
exactly solve anymore the Hamiltonian. So this two-body approximation is basically an approximate technique to get, let's say, some knowledge about the spectrum,
Mm.
even though you cannot resolve the whole spectrum of the Hamiltonian.
Okay, so I understand. So when you have non-zero hz,
Yeah.
what kind of properties do you want to calculate or do you want to get? Just such as relaxation time or
Say that again. Sorry, please. Can you say the last thing again?
so when hz is non-zero,
Uh-huh.
so you said the system is going to some equilibrium state.
Yeah. So when hz is equal 0, so imagine, maybe you can go back to this picture. Okay, maybe this is actually useful, okay? So the first part, okay, so basically you turn on hz, so the longitudinal field, and then you get this energy imbalance, okay?
Mm-hmm.
But what we did in this first part, somehow, we were basically studying, because basically we were still close enough to the true ground state. Because of the quench protocol, we kind of stayed in this like true ground state, close enough to the true ground state. Only like a little bit above, enough that you are not anymore in an eigenstate, but you have an overlap of different eigenstates, such that you get this dynamics. But what are these eigenstates, if you want? Even though we don't have like a complete knowledge of the spectrum, we still know somehow, and this is why I did this, like I show you this like two-domain wall picture. We know that at least to some extent, this first excited states on top of the true vacuum, there should be described by these like two-domain wall pairs constrained by a string. Maybe I can go back to that. Constrained by a string, which is an energy price that you pay because of this finite energy difference that is introduced, when you turn on the longitudinal field. So essentially, this gives you some effective string, which is like linearly increasing. So it's an energy price which is linearly increasing with the number of flipped spin that is between these two domain walls, that bounce these domain walls into this confined dynamics. And even though we don't have like we cannot exactly solve the problem, we still know that when we are close enough to the true ground state, we are populating these modes. And by populating these modes, we see this like some kind of more exotic dynamic than the standard quench dynamic that I showed you. So basically, the standard quench dynamic in this case is like this propagation of particles that is detectable in these like correlations, and local of this strange behavior of local expectation values, which, by the way, when you Fourier transform, you really see that you have like specific peaks that are exactly, if you want, like you can model these peaks in this way, and you see that it's working essentially. So you really see in this way that you are populating these modes that are like in over the true ground state. So this is more or less, I don't know if I answered your question. I hope it's like
Okay.
at least
Okay.
clear.
Anyway, yeah, I will listen your talk. So
Mhm.
yeah, go ahead.
Yeah, okay. So basically now in the second part, we are trying to modify our like quench protocol such that we are not anymore close to the true ground state, but we are in some state that we understand as false vacuum, in this sense. So basically we try to be close to the state, to the configuration, which is like metastable. So essentially, okay, maybe it's useful to go back here. So if you go back to the picture that we had here, so depending on the sign of this longitudinal field, what happens is that these polarized states, when you turn on the original field, one gets an energy price with respect to the other one because it's like unfavored configuration. This unfavored configuration is what we call false vacuum. Now we'll try to prepare the state close enough to this unfavored, energetically unfavored configuration. And we try to see what happens under unitary dynamics. And this is what we understand. Sorry, I went in the opposite direction. We understand as false vacuum decay in this setup. So, pardon. Okay. So we want to study this tunneling process, but tunneling of not a single particle, tunneling if you want, but tunneling of a many body problem, okay? And for us, what is this false vacuum decay? So we prepare initial state to be, as I said, this like a metastable state. We perform unitary time evolution, and then we can see that this the probability to stay in this configuration is decaying with time. So there are other contributions. But there is some contribution which is suppressing this probability to stay in this initial state. And then we are trying to understand if on this kind of model we can characterize this parameter, so this decay rate. So the underlying idea, so again, in this like simplified, fully polarized game, is the following. So you start from this false vacuum, which is at certain energy 0, and then you start flipping spin, okay? But the flipping of spin, it's happening. So as we said, the dynamic is given by the transfer field, so Hx. So any action of flipping of the spin is given by this transfer field. So the first part is when you nucleate a small bubble, imagine this. But this brings you up over the barrier, okay? Because now you have created the two domain walls, and then you have paid this energy price, which is given by the mass of these two main walls. But then you keep flipping, and then you will increase the domain. But in this case, something different is happening from before, because before we were saying that the flipped configuration between domain walls were like giving some energy price. In this case, we are working like in the opposite sign of the longitudinal field, so we're getting some energy gain. So the more the domain is expanding, the more energetically favored we are, until at one point we need to reach something, which is, say, the exit point, which is our critical bubble. And the critical bubble is essentially, I flipped enough spin, let's say, such that I am the same energy level as the forced vacuum before, so the state from where I started. So this is to get some intuition of perturbative, let's say, because in this small hx limit, we can kind of understand this perturbatively in the hx limit. And we can understand basically that intuitively, I have to flip this number of spin in order to get to the critical bubble. But what does it mean? So I have to flip this number of spins. So basically, if you want, in this small hx limit, in the end, you get to flip an exponential number of, so in perturbation theory, you need to have like so many steps, you know, between these two that you, in the end, you get this exponential expression. And because of the fact that like the number of spin that you're flipping is going like in this way, so from 1 over hz, you understand why there is this dependence on 1 over hz of your decay rate. But then, okay, you can be more general. And if you want, I have prepared a sketch of this, like of basically. So the thing is that, okay, now we can do two things. So either you trust this result, and basically I just show you more or less the numerical work that we did. And then maybe if you want later, if you have time and you want to know, I can give you some more detail on the derivation. Otherwise, I will give you the details on the derivation right away. What you prefer?
Just it's up to you.
It's okay.
Yeah.
I mean, I think I should do. Let's go to the phenomenology. Maybe if you want, I can like if you have time, I can explain a bit more of the derivation. Okay. So just understand that this, you have this functional form that we understand intuitively in this way, but we can be more generic under certain assumptions. Basically, that this like energy difference between the vacuum, let's say somehow it's like small with respect to the energy gap that you have to do, so the energy mass of the particles. Under this assumption, basically we can get like a more generic expression which has still this functional form, okay?
Mm-hmm.
And what we did, okay, so essentially we devised this quench protocol. So you write your system like in the full polarized state again. But then basically we perform some adiabatic, if you want, like some imaginary time evolution to let the state relax to this vacuum, and then we change the sign of the longitudinal field such that this state goes into the unfavor of the configuration. The reason why we perform this like imaginary time evolution is that in this case we want to neglect the effect of the transfer field in the quench. So the kick that we give to the system with the transfer field in the quench, we want it to be as small as possible because we only want to detect the effect of the instability of the state due to the change of sign of Hz, so of the longitudinal field. We don't want to kick the system by changing the transfer field like we did before, basically. And then what happens is that we need to find some, let's say, because the thing is that in the quench dynamics, you have like some short-time dynamics, which is governed by the off-resonant states. So basically, we're far away from having like a resonant bubble, so these like critical bubbles. And then basically, we have the time scale of the decay, which is the one that we want to detect. And then afterwards, essentially the system will thermalize in the sense that I showed you before. So basically, after a while, you will have a secondary process. And because the easy model, when you add the longitudinal field, is not anymore so integrable model, so you don't have any more infinite number of conserved quantities, what happens is that it goes in the case of thermal system. So in the system that after a while, the dynamic will become thermal. So locally, the deduced density matrix, or if you want, all local observables are described by this thermal ensemble. This stage also we do not want to see. We want to see this intermediate stage, and this is basically what we had to do, basically tune Hz and Hx such that we had a clean separation of timescales. to find eventually this part in the simulation that we could assume that we are observing this like a tunneling process, okay? And how do we do this? So after the quench, so we start from this state that, as I said, we prepared by this from the full polarized states, and then with this imaginary evolution, we compute these two objects. But I mean, I will focus on the second one. It's more intuitive. It's still like a local magnetization of the system. It's just rescaled somehow such that it starts from 1, okay? And then when you go to the other side, eventually it goes to 0. And then this quantity, we like compute it numerically for different value of the longitudinal field in order to extrapolate the dependence of the longitudinal field. And then we basically assume this functional form of these two quantities, and we perform a fit. And then by fitting, we extrapolate these decay rates. Second thing we did is that we had this theoretical prediction that I explained to you intuitively before. We tried to compare it with the theoretical prediction with the data extrapolated from the numerics for different value of the transfer field. You can see that we are going pretty close to the phase transition, because the problem is that here, if we stay with the transfer field close to 0, the dynamic is too slow. So basically, this is not possible. It would be impossible to observe in this kind of numerics. But also, you have to find a balance, because so we know that this numerics, it's like has problem when you start building up too much quantum correlation in the system. So we had to find a mirror, you know, a window. Sorry, I like a very good window to see this. And we try to compare with the theory. The thing is that, so the shift is given by the prefactor, but the slope is given by the thing that is inside the exponential. So overall, what we observed is basically that what it's in the exponential, and then we try to compare it like more accurately here. It's like nicely overlapping with the theory, while the prefactor is we're not completely. I mean, here and here it was off, but by, let's say, almost 1 order of magnitude. So so the good thing is that we have a nice overlap of what we can extrapolate by assuming this functional form from this fit, and comparing with this, which is the theoretical prediction. It's well aligned, but the prefactor is a bit off. So this is more or less the main result, okay? But the thing is that we could find, let's say, somehow this universal exponential component. Okay, so this is more or less the main result of the paper. Then, okay, this is like a short parenthesis on another work, but maybe you can skip. In the paper, there is another part where we use another model, basically, which is the ladder. So I think conceptually it's interesting just because in this case, so it doesn't change much. What is interesting with this model is basically that you have like a more complicated model. So on because essentially it's this 2 XX chain coupled by this Ising-like coupling. What is interesting is because this model has 2 features. One is that it's not anymore possible. So even when delta, so this coupling is 0, you cannot solve this model by free fermion mapping. The thing is that if you map this to fermion, what you get from here is like the Hamiltonian is not quadratic anymore in the fermion. So you cannot solve it then by Fourier transform and doing Bogoliubov rotation, because you will get this interaction. So these are like a term, what do you say? These are these are interaction terms. So you have 4 times the fermionic field. So to treat this exact chain, there are integrable techniques that are called bad ansatz. But it's interesting, okay, because it's like a more complicated structure. You cannot like imagine this model as a free model, so like free particle models, like free fermion, like before. The second thing is that because of this like quasi one-dimensional structure, essentially you have like 4 degenerate ground state. And what happens is that when you turn on this field is basically, this field is actually playing the role of the longitudinal field in the Ising model. But you break the degeneracy between only 2 pairs of ground states. So overall, you're left with some degeneracy. And because of this degeneracy, basically, you get like a more interesting particle content. But in the end, what we did is that you still get this, let's say, picture of confinement because of this original field. And also, we address the problem of false vacuum decay. But in this case, of course, like we just tested this functional form because we don't have an underlying theory that gives us like what we should have in the exponential. Okay, we just tested this idea that somehow the decay rate should behave like as exponential of -1 over the field that is creating the energy imbalance between the 2 ground states, in this case between the 2 pairs of ground states, because they are 4. And we could see that we can find like a regime where we can isolate, let's say, at least to 1 order of magnitude, when they can isolate this functional form, okay? And this, let's say, the main content of this this work on false vacuum decay in quantum spin chain. So may I ask you, so now so here there is some part of possible, let's say, so let's say somehow this is the idea what's next, okay? So to some extent, there are already works like this one that I showing you, where people basically are studying with like these numerical techniques that are very efficient with spin chain, problems of scattering between bubbles. There are also works that are studying, addressing the problem of scattering between mesons. Then there is this interesting work where basically they worked in the field theory. So in the Ising field theory and the generalization of Ising field theory, and they performed some kind of analysis which is like similar to ours, but it's like a numerical technique which is suitable for field theory. And then basically draw the same conclusion as us. Basically, they were able to test the dependence in the exponential, and they managed to get like a nice result with the factor in the exponential, but they could not match the prefactor. So one thing to say is that, let's say, this prefactor probably is not like completely understood so far. And then there is, okay, this other experiment, interesting experiment with this. It's recent. It's like they work in this limit, which is quite different from the limit of our numerics, because they are working in the small transfer field limit, but they are testing some nice effect. So because in the small transfer field limit, what you can do, maybe this is easy to understand like from this picture. In the small transfer field limit, what you can do is that by changing this longitudinal field, you can basically match exactly, because this, in principle, this matching of the false vacuum with the critical bubble, when you are in the small hx limit, it's not always there. So you can change the hz, and basically by changing hz, you can find a way to decide which is the size of the critical bubble that is matching your initial energy of the false vacuum. And what's nice basically is that they observe resonances by changing the longitudinal field when exactly, for example, the length equal to bubble, it's matching the initial state. Then when they change even a bit more the longitudinal field, and then they observe the resonance at 3, and then they observe the resonance at 4, and so on and so forth. Because on the other side of the barrier, basically they are changing the longitudinal field such that they are deciding which of these bubbles is going to be the critical bubble, but in a limit where the critical bubble is very small. So it's like kind of opposite, because our like analytical treatment here works in a limit where the critical bubble is very large. In this limit, the critical bubble is very small, but it's nice that they can observe on this like Rydberg atom experiment. They can observe this resonance in this process, in this tunneling process. So at this point, I would say that I more or less said the majority of the content of the work, of this work on false vacuum decay. If you want, I can give you, depends on you. I mean, still have some time, but I'm running a bit long. So I think it's time for questions. And if you want to know a bit more, what's the underlying theory between, let's say the underlying theory of this computation of the decay rate, I can give you these details if you want. I mean, it's up to you at this point. Thanks for your attention. Okay.
Thank you so much for nice talk and passionate talk. Yeah. Actually, since because of your good explanation, I tried to understand your talk, but since my major is particle physics, yeah, so I couldn't understand fully about your talk. But I personally I got the mainstream of your work. Yeah, so yeah, actually I have several questions, but before I ask you, in the attendee, there are several questions or comments. Yeah, actually during your talk, we have exactly 8 attendee, but I think because of now the time is quitting time, yeah, so many fellows go out. So please understand this point. Yeah, I'm sorry about it. Yeah.
No, I mean, I'm sorry for running late.
No. It's completely okay. Yeah. Since
I mean, it's
because
also
of yeah.
yeah, I'm sorry I had that stupid technical problem at the beginning, by the way, and then I lost time.
No. Your explanation was very good. So since there is no question, I'm gonna ask you several questions. Actually,
Okay.
I have my question is a very naive one.
Okay.
In almost the last of your talk, you also considered another Hamiltonian with the additional Hamiltonian term, which is
Okay.
given by the delta perpendicular sigma z and sigma z.
Yeah, this other model, let's say.
Yeah, other model. Yeah. So yeah, my question is my very naive question is how can I imagine the system described by this Hamiltonian? Definitely, I can imagine the kind of lattice structure or crystal. Yeah,
I
then
mean,
mm,
there are, I mean, like, these are, I mean, of course, these are always idealized models, okay? But there are models where at the microscopic level, they are rather like there are material that were ferromagnetic material that they're understood as like these chains coupled. So usually they're kind of a Heisenberg, if you want, Heisenberg interaction over the one axis and also over the other one axis, okay, with some asymmetry, okay. So let's say imagine you have like a longitudinal direction and like say this like if you want like orthogonal direction. This XYZ ladder is still some kind of generalization of the Heisenberg model. It's just that you have this parameter that will give you a symmetry. If this parameter is 1, you get back to the Heisenberg model, okay? You see this? Because the Heisenberg model is basically, it's like S scalar S.
Yeah, yeah,
So okay, so basically this is like XX, Y, Y, Z, Z. So this is a scalar product. Then you put some asymmetry. There are some material that they show this kind of asymmetry. I mean, I'm not an expert of this because I'm not entirely in solid state physics, but I know that like there are some material that are showing this. And they can also, at the microscopic behavior, there are materials that are described by this like coupling between like two chains, if you want, coupled together. This is like not something that exotic. This is like observed. Actually, when I showed you at the beginning, like here, this experiment with the neutral scattering, I don't remember which one of these. It's made with not with the Ising model, but with one of these, let's say, quasi one-dimensional ferromagnets. Actually, maybe anti-ferromagnet. So actually, all this picture works either you are like a ferromagnetic ordered or also anti-ferromagnetic ordered. This is not a problem. You can also have like this anti-ferromagnetic structure, up, down, up, down. So, and they did this experiment and they observed these resonances when you put like this external field. So this is not that exotic. The model, of course, that I'm using, it's a bit idealized maybe, but so I don't know exactly which material could be compatible with that, but it's the idea of XXX chain, so spin chains that are coupled in a ladder. It's present because some material are well described by this approximation at the microscopic level.
Considering such Hamiltonian looks natural, right? You mean?
Kind of, yeah.
Yeah, yeah,
But
yeah.
the way you should think now, so the main message that they will give you now at this point is that, so of course, things started with observation and then people started to model observation. But now the things now are going somehow the other way around, to sense, because the experimental setup are getting better and better and at fine-tuning specific many-body problems, okay? So the thing is that, okay, we have this spin chain. People did all sort of theoretical exploration of this spin chain. So there are many exact results. So there are many numerical results. So we can give these results to experiment, to benchmark, and the experiment are fine-tuning these problems, okay? So the thing is that everything that the spin chain is like somehow natural mapping to this like quantum devices because of this idea of local, let's say, so when you are at quantum computation, your building block is this so-called computational basis. The computational basis is like a one-to-one mapping with the spin configuration because up-down spin is 0-1 basically.
Yeah.
So any phenomena that is like well understood on a spin chain, it's a challenge at this point for a quantum device to simulate it and see how good it is at simulating, because on the other side, they have a good benchmark coming from the theory. That's the idea. So if we can if we find some interesting phenomena on a spin chain, then it's interesting to test it on the device. So even though there are materials, okay, so there is still some one part of the community is modeling like the materials. In this case, let's say in the more theoretical perspective, what we're interested in is to get to a point where these devices are getting better and better on simulating the dynamics of fine-tuned models. So we say theoreticians are saying experimentalists realize this spin Hamiltonian, realize this spin model, okay, and try to see this effect, okay. This is going the other way around at this point. And this, if you want my personal opinion at this stage, okay, for the future, I mean, I don't know how much it makes sense, but the thing is that from a spin model, okay, you can always perform the scaling limit and go to the field theory. The thing is that, so if we have some interesting phenomenon that is well understood on a spin chain and is tested on an experimental device, at one point this experimental device, they will be good enough and big enough to perform a scaling limit to give some prediction of the underlying field theory of the problem, okay? I don't see why this shouldn't happen at one point. in the same
Ah,
fashion as lattice field theory, you know. I mean, sorry, yeah, lattice field theory, you know. If you do lattice quantum chromodynamics, you discretize the problem, you put it on a lattice, you perform the simulation, and then
yeah, yeah.
you go to scaling limit and you extrapolate to field theory, okay?
Yes.
From the point of view of the energy physics, what people are trying to do is this on quantum devices. So yeah, they're trying to get better and better and at simulating, let's say, many body problems. And at one point, it will be possible to upscale this lattice because they are naturally on a lattice, of course. But then when it will be big enough and tunable enough, it will be possible to perform the scaling limit and extrapolate results on the field theory.
I see. Yeah. By the way, what you said is just the I think it is very similar to the usual theory guy do. Usually, what theory guy would do, right? Yeah, just to make a model and then just
Yeah,
investigate it,
exactly.
and then
Yeah.
just give it our model to experimentalist to be checked. Yeah.
Exactly. So that's yeah, that's more or less the idea. So I started from the experiment, so from the observation, but now everything is going the other way around. So these models are theoretical models, abstract in a sense, but they can be tested, and they are already tested to some extent in the experimental setup. I mean, here I also had some example, for example, for this confinement stuff. So this, for example, on the right, this is very evident. So this is like the effect of this like a secondary propagation when you turn on the longitudinal field. So you have this shrinking of the light cone because as I said, now we have like these mesons propagating and not the free particles that are heavier. And this is an IBM quantum computer. This is like this is an IBM quantum. This is like super cooled qubit. It's basically a quantum chip where they simulated the easy model and they were able to observe this effect. Okay, this is one. I mean, the work, there are other results. So, for example, there are some results that are already tested here. And now there are many actually experimental confirmation of many theoretical prediction. You know? So, for example, all these things that at one point I explained you of the thermalization of this closed quantum system, it's a whole theoretical exploration that started at one point because people started to understand this effect, okay? Because we understand, so this is like a whole subject because of course we understand, I mean, maybe there is a message in the chat, I don't know.
Yeah, Professor Ko, Pyong Ko has to leave. Yeah, so
Okay, it's
yeah,
okay.
he leave the message. Yeah.
So it's like a whole subject that started because of the experimental advances, but in the sense that people said, okay, there is hope that we can observe this because the experiments are getting better and better. So there is hope that we can really realize a pure unitary evolution. Of course, you cannot be always pure unitary, okay? Because the experiments at one point, they will have some noise. But exceed that they have like a long enough time window where the dynamics it's approximately unitary and the system is like approximately closed where they can test this effect. And then people started to understand that, okay, the system is closed. We usually understand thermal theory as like system coupled to a bath, right? But there is some mechanism for which this system locally, they're still relaxing to some thermal ensemble, and this is like a whole subject. And at one point, people started to understand that what happens is that the complement of the system, so as explained here, basically, where is it? The complement of the idea is basically to summarize that the complement of the system is behaving like a bath for the subsystem. If you wait enough time, and you know, when you have a well-defined quasi-particle context, it means that the quasi-particle have traveled enough locally, this subsystem can thermalize in this sense. And what you understand is like the complement of the system is, so the other part of the system is behaving as a bar. And then, okay, as I say, so this like this diverging a bit from the main topic, okay, but just to explain you that like this everything purely theoretical and then has been checked, you know, even though these spin models are coming from some, let's say, solid state condensed matter perspective, then they nucleated, if you want, long story of theoretical speculation that went in a completely different direction, and now it's like a problem to be tested and engineered on tabletop experiment, basically. Okay.
I see. Yeah, yeah. Thank you so much.
It was a
I
pleasure. I mean,
I don't know. I was very happy to invite you, and then I was very surprised because your talk was very passionate. Yeah, so it was very very happy to hear your talk. Yes.
yeah, thanks.
Yeah, thanks. And then maybe you woke up early because of this talk, right?
You?
You woke
No,
up
I mean,
early.
yeah, no, I mean, not that early. I mean, it's not, I mean, it was 9 in the AM. No, it's not like 6 in the AM. It's fine.
Okay, okay. Uh, okay, I see. Then
Yeah.
maybe in a few days, our staff will contact you to give a honorarium.
Mhm.
Yeah, yeah.
Okay.
So yeah, just please wait. Then maybe our staff will send you email. Yeah,
Okay,
for
okay.
your C, yeah, or your CV or other document. Yeah, maybe our staff will require you. Yeah.
Okay, okay, okay. I mean, okay,
Yeah, yeah.
sure.
And then yeah, maybe you can find your talk in our YouTube. Yeah.
Okay, okay.
Yeah.
Nice.
Okay, thank you again. I really, really I appreciate for having you in
No, no,
this seminar. Yeah.
thank you for inviting me. Yeah, yeah, it was very
Thank you
nice.
so much. Okay, okay.
Yeah.
Okay, then see you.
I hope to see you. Take care.
Yeah,
Bye
I
bye.
hope to. I hope to. Yeah. Bye. Bye.
Bye.
Yeah.